In this video, we will discuss estimating a population standard deviation or variance. Here are key points about the chi-square or chi-squared distribution. In a normally distributed population with variance sigma squared, if we randomly select independent samples of size n, and for each sample compute the sample variance s squared, the sample statistic chi-squared equals n minus 1 s squared divided by sigma squared, has a sampling distribution called the chi-square distribution. Critical values of chi-squared. We denote a right-tailed critical value by chi sub r squared, and we denote a left-tailed critical value by chi sub l squared. Those critical values can be found by using technology or table A4 on page 687, and they require that we first determine a value for the number of degrees of freedom. For the methods of this section, the number of degrees of freedom is the sample size minus 1. The chi-square distribution is skewed to the right, unlike the normal and t distributions. The values of chi-square can be 0 or positive, but they cannot be negative. The chi-square distribution is different for each number of degrees of freedom. As the number of degrees of freedom increases, the chi-square distribution approaches a normal distribution. Because the chi-square distribution is not symmetric, a confidence interval estimate of sigma squared does not fit a format of s squared minus e is less than sigma squared is less than s squared plus e. So we must do separate calculations for the upper and lower confidence interval limits. If using table A4 for finding critical values, note the following. In table A4, each critical value of chi-square in the body of the table corresponds to an area given in the top row of the table, and each area in that top row is a cumulative area to the right of the critical value. Table A2 for the standard normal distribution provides cumulative areas from the left, but table A4 for the chi-square distribution uses cumulative areas from the right. A simple random sample of 22 IQ scores is obtained. Construction of a confidence interval for the population standard deviation sigma requires the left and right critical values of chi-square corresponding to a confidence level of 95% and a sample size of n equals 22. Find chi-square sub L and chi-square sub R, the critical values of chi-square separating an area of 0.25 in the left and right tails respectively. With a sample size of n equals 22, the number of degrees of freedom is n minus 1 equals 21. The critical value to the right, chi-square sub r equals 35.479, is obtained from table A4 in a straightforward manner by locating 21 in the degrees of freedom column at the left and 0.025 across the top row. The leftmost critical value of chi-square sub L equals 10.283 also corresponds to 21 in the degrees of freedom column, but we must locate 1 minus 0.025 equals 0.975 across the top row, because the values in the top row are always areas to the right of the critical value. When obtaining critical values of chi-square from table A4, if a number of degrees of freedom is not found in the table, you can be conservative by using the next lower number of degrees of freedom, or you can use the closest critical value in the table. For numbers of degrees of freedom greater than 100, use the equation given in exercise 23 on page 342, or find a more complete table of chi-square values online. Although chi-square is the best point estimate of sigma squared, there is no indication of how good it is. So we use a confidence interval that gives us a range of values associated with a confidence level. We use the following notation. Sigma equals population standard deviation, sigma squared equals population variance. S equals the sample standard deviation, and S squared is the sample variance. N is equal to the number of sample values. E is the margin of error. Chi-squared sub L is the left-tailed critical value of X squared, chi-squared, and chi-squared sub R is the right-tailed critical value of chi-squared. The sample is a simple random sample, and the population must have normally distributed values, even if the sample is large. The confidence interval for the population variance sigma squared is n minus 1 times s squared over chi squared sub r is less than chi squared is less than n minus 1 times s squared over chi-squared sub L. The confidence interval for the population standard deviation sigma is square root of n minus 1 s squared over chi-squared sub r is less than sigma is less than the square root of n minus 1 s squared over chi-squared L. The round-off rule for original data, when using original data set of data values, round the confidence interval limits to one more decimal place than is used for the original data. The summary for summary statistics, when using summary statistics n and s, round the confidence interval limits to the same number of decimal places used for the sample standard deviation. Confidence intervals can be easily constructed with technology, or they can be constructed by using table A4 with the following procedure. First, verify that the two requirements are satisfied. The sample is a random sample from a normally distributed population. Using n-1 degrees of freedom, find the critical values chi-squared sub r and chi-squared sub L that correspond to the desired confidence level. To get a confidence interval estimate of sigma square, use the following. n-1 s squared over chi-squared sub r is less than sigma squared, which is less than n-1 s squared over chi-squared sub L. To get a confidence interval estimate of sigma, take the square root of each component of the above confidence interval. Round the confidence interval limits using the round-off rule given in the key elements. Confidence intervals can be used informally to compare the variation in different data sets, but the overlapping of confidence intervals should not be used for making formal and final conclusions of variances or standard deviations. A certain data set lists IQ scores for subjects in 3 different lead exposure groups. The 22 full IQ scores for the group with medium exposure to lead have a standard deviation of 14.29263. Consider the sample to be a simple random sample and construct a 95% confidence interval estimate of sigma, standard deviation from which the sample was obtained. Requirement check. The sample can be treated as a simple random sample. The accompanying histogram has a shape very close to the bell shape of a normal distribution, so the requirement of normality is satisfied. Using table A4, we first use the sample size of n equals 22 to find degrees of freedom. The degrees of freedom are equal to n-1, which is 21. In table A4, refer to the column corresponding to 21 degrees of freedom and refer to the columns with areas of 0.975 and 0.025. The critical values are chi-squared sub L equals 10.283 and chi-squared sub R equals 35.479. Using the critical values, the sample standard deviation of S equals 14.29263 and sample size of n equals 22. We construct the 95% confidence interval by evaluating the following. n-1 times s squared over chi-squared sub r is less than sigma squared is less than n-1 times s squared over chi-squared sub L. So 22 minus 1 times 14.29263 squared over 35.479 is less than sigma squared is less than 22 minus 1 times 14.29263 quantity squared over 10.283. Evaluating the expression results in 120.9 is less than sigma squared, which is less than 417.2. Finding the square root of each part before rounding, then rounding to one decimal place yields this 95% confidence interval estimate of the population standard deviation. 11.0 is less than sigma is less than 20.4. If we select random samples of size n from a normally distributed population with variance sigma squared, there is a probability of 1 minus alpha that the statistic n-1 times s squared over sigma squared will fall between the critical values of chi-squared sub L and chi-squared sub R. It follows that there is a 1 minus alpha probability that both of the following are true. n-1 s squared over sigma squared is less than chi-squared sub R, and n-1 s squared over sigma squared is greater than chi-squared sub L. Multiply both of the preceding inequalities by sigma squared, then divide each inequality by the appropriate critical value of sigma squared, so the two preceding inequalities can be expressed in these equivalent forms. N minus 1 sigma squared over chi squared sub r is less than sigma squared, and n minus 1 times s squared over chi squared sub l is greater than sigma squared. The two preceding inequalities can be combined into one inequality to get the formula of the confidence interval used in this section. N minus 1 times s squared over chi squared sub r is less than sigma squared, is less than n minus 1 times s squared over chi squared sub l. The procedures for finding the sample size necessary to estimate sigma are much more complex than the procedures given earlier for means and proportions. For normally distributed population, Table 7-2 on page 338 or the formula given in exercise 24 on page 342 can be used. StatDisk also provides sample sizes. With StatDisk, select Analysis, Sample Size Determination, and then Estimate Standard Deviation. Minitab, Excel, StatCrunch, and the TI-83 and 84 Plus calculator do not provide such sample sizes. We want to estimate the standard deviation of all IQ scores of people with exposure to lead. We want to be 99% confident that our estimate is within 5% of the true value of sigma. How large should the sample be? Assume that the population is normally distributed. From table 7-2, we can see that 99% confidence and an error of 5% for sigma correspond to a sample size of 1,336. We should obtain a random sample of 1,336 IQ scores from the population of subjects exposed to lead.